There is something wrong with the universe. Not wrong in the way a broken machine is wrong. Not a malfunction you could point to. A gear misaligned. A circuit shorted. Wrong in the way a dream feels wrong when you are still inside it. Everything is coherent. Everything follows its own rules. And yet something underneath refuses to settle. Something hums at a frequency just below the threshold of language. You cannot name it. But once you feel it, you cannot unfeel it. Physicists have been feeling it for decades. It began, as many great disturbances do, with a question that seemed almost too simple to take seriously. What is matter at its deepest level? Not what it looks like, not how it behaves in bulk, but what is it when you strip away every layer of complexity until nothing remains but the irreducible core? For centuries, the answer was atoms. Then it was protons and electrons, then quarks, then fields. Each answer was smaller, stranger, and harder to visualize than the one before. And then, at the very bottom of the excavation, physicists found something that stopped them cold. They did not find a smaller particle. They did not find a simpler field. What they found, what the mathematics forced them to confront, was that matter, at its most fundamental level, does not behave like matter at all. It behaves like information. An electron, before it is observed, does not have a position. It does not have a definite momentum. It exists in what physicists call a superposition, a smear of all possible states simultaneously, a ghost of probabilities haunting a volume of space without committing to any particular point within it. The electron is not somewhere, and you just don't know where. It is genuinely, mathematically, experimentally nowhere in particular. It is a question that has not yet been answered. And the moment you look, the moment a measurement is made, the moment the universe is forced to respond, the question collapses into a single answer, and the electron appears, definite and located, as if it had always been there. This is not a philosophical interpretation. This is not a debate among theorists about what equations mean. This is the most precisely tested prediction in the history of science, confirmed to a degree of accuracy that makes every other measurement in physics look like a rough estimate. The universe, at its base layer, only decides what it is when something looks. Sit with that for a moment. Really sit with it. The chair beneath you exists because you are part of a vast web of interactions, particles bouncing off particles, fields coupling to fields, an unbroken chain of observations stretching back to the Big Bang. But the chair, in the deepest sense, is not made of wood or plastic or metal. It is made of answers. Answers to questions the universe asked itself billions of years ago, and answers it is asking right now, at a scale so small, no instrument will ever reach it. You are not sitting in a room full of things. You are sitting inside an ongoing computation. And here is where the discomfort begins to sharpen into something else, something closer to vertigo. Because if the universe computes its own contents, if reality is, at some fundamental level, the output of a process rather than the substance of a stage, then the next question is not merely scientific. It is not a question you can dissolve into an equation and file away in a journal. It is a question that reaches through the mathematics and grabs you by something you do not have a name for. Who is running the process? Or, and this is the version that keeps physicists awake, what if the right question is not who, but when? What if the process is not something that happened at the beginning and then ran on its own? What if it is happening now, continuously, updating in real time? And what if, in ways we are only beginning to detect, it is getting better at what it does? If you find yourself drawn into questions like this, if you are the kind of person for whom a crack in the surface of the obvious is an invitation rather than a warning, then stay here. Leave a like, subscribe to the channel, and let's follow this thread together, because what it leads to is not a comfortable place, but it is an honest one. The story of the simulated universe is not a story about computers. It is not a story about science fiction. It is a story about the nature of reality itself. And it begins not in a laboratory, not in a philosopher's study, but in the one place you have always, quietly, suspected, held the deepest secrets of all. It begins when you look too closely at what is actually there. In the early 20th century, when quantum mechanics was still young and its founders were still alive to be disturbed by it, there was a standard way of managing the discomfort. You were told, by textbooks, by professors, by the culture of physics itself, that the strangeness of the quantum world was a feature of the very small. Electrons behaved like probability clouds, yes. Particles existed in superposition, yes. But the macroscopic world, your world, the world of tables and trees and planetary orbits, was safely classical. The weirdness stayed downstairs. You lived upstairs, in the ordinary. That story has been quietly falling apart for 50 years. The boundary between quantum and classical, it turns out, is not a wall. It is a gradient. The process by which a quantum superposition becomes a definite classical outcome, called decoherence, is real, and it explains why your chair does not flicker between states. But decoherence is not a resolution. It is a description of how the appearance of classicality emerges from quantum mechanics. The underlying layer is still quantum. The underlying layer is still probabilistic. The underlying layer is still, always, at every scale, at every moment, a computation in progress. And that computation has a resolution. This is the part that should make you stop. Because in 1899, the physicist Max Planck, while working on a completely different problem, stumbled onto a set of natural units, units of length, time, and mass, defined entirely by fundamental constants of nature. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. The Planck time is approximately 5.4 times 10 to the power of negative 44 seconds. These are not merely very small numbers. They are, according to our best current theories, the smallest meaningful sizes that space and time can have. Below the Planck length, space itself loses definition. Below the Planck time, the concept of before and after ceases to apply. In other words, reality is granular. It comes in minimum units. It is pixelated, not as a metaphor, not as a loose analogy, but as a precise technical claim about the structure of space-time itself. And pixelation is not a property of nature. It is a property of rendered systems. Every screen you have ever looked at, every digital image you have ever seen, every video game environment that has ever surrounded you, all of them are pixelated because they are computed. The resolution is a consequence of the computational substrate. There is always a smallest unit, because there is always a limit to what the hardware can resolve. The universe has a smallest unit. This does not prove we live in a simulation. Nothing proven here, nothing settled, nothing resolved. But it does mean something that physicists have only recently begun to say out loud in polite company. The structure of our universe is formally identical to the structure of a computed system. The mathematics that describes our physical reality and the mathematics that describes a sufficiently complex simulation are, at this level of analysis, indistinguishable. You may choose to find that reassuring on the grounds that it changes nothing about your daily life. The coffee is still hot. The morning is still morning. The people you love are still real in every sense that matters to the living of a life. But the question, once asked, does not wait for your permission to keep unfolding. Something is computing this, and whatever it is, it has been at it for approximately 13.8 billion years, refining, expanding, elaborating, producing from a set of initial parameters so precisely calibrated that even a fractional deviation in any direction would have guaranteed a universe of nothing but darkness and formless gas, the exact conditions necessary for stars, for planets, for chemistry, for consciousness, for you sitting here in a chair made of answers, reading a question that may be the most important one your species has ever asked. What exactly are you inside of? Let's try to hold this in your hands for a moment. Let's try to make it real. Not in the way abstract physics is real, floating somewhere between the equations and the incomprehensible, but in the way a stone dropped into still water is real, immediate, visible, traceable. Imagine you are playing a video game. Not the kind we have today. Not the games with their beautiful, but obviously artificial landscapes, their rigid geometries, their textures that repeat if you look too closely at the corner of a wall. Imagine a game built by a civilization 10,000 years more advanced than ours. A civilization that has solved every engineering problem we have ever dreamed of solving, and then solved 1,000 more we haven't imagined yet. Their simulation is not a game in any sense you would recognize. It is a universe, complete, self-consistent, running on hardware so far beyond your comprehension that the comparison between their processors and yours is less like comparing a supercomputer to an abacus and more like comparing the sun to a matchstick. In this simulation, every particle behaves according to precise mathematical laws. Every interaction is computed. Every field propagates according to equations. The inhabitants of this simulated universe, if it has inhabitants, do not see the substrate. They do not feel the processing. They experience only the output, a world of apparent solidity, apparent causality, apparent continuity, a world that feels, from the inside, exactly like reality. Now ask yourself, how would they know? This is not a new question in philosophy. René Descartes asked a version of it in the 17th century when he entertained the possibility of an evil demon powerful enough to deceive all his senses. But Descartes' demon was a thought experiment with no physical texture. The modern version is different. The modern version has teeth because it is grounded not in skeptical whimsy, but in concrete physics, in information theory, in the actual trajectory of technological development. And it leads somewhere Descartes never went. It leads to numbers. In 2003, the philosopher Nick Bostrom published what has since become one of the most quietly devastating arguments in contemporary philosophy of mind. He called it the simulation argument, and its logic is, at its core, almost brutally simple. Either almost all civilizations that reach a sufficient level of technological sophistication destroy themselves before developing the capacity to run realistic simulations of minds, or the overwhelming majority of civilizations that could run such simulations choose not to, or the vast majority of minds in existence are simulated. One of those three things must be true. They exhaust the logical possibilities. And if neither the first nor the second is true, if some civilizations survive their own advancement, and some of them choose to build simulated worlds, then the third follows with the cold inevitability of arithmetic, because a single advanced civilization could run not one simulation, but millions, billions. The ratio of simulated minds to original minds would be, over any significant stretch of cosmic time, so lopsided that the probability of any given conscious mind being an original rather than a copy approaches zero. This is not a scare tactic. It is a probability calculation. and probability calculations do not care whether you find them comfortable. But let's stay with the human scale a while longer, because the abstraction can make it easy to keep the argument at arm's length, to appreciate it as clever without really feeling its weight. So try this instead. Right now, in this moment, you are having an experience. You are reading words, and behind the words there is something, a sense of presence, a quality of awareness, a perspective that is unmistakably yours. This is the central fact of your existence, more certain than any external reality, that there is something it is like to be you, right now, in this moment. Philosophers call this phenomenal consciousness. Everyone else calls it simply being alive. Now consider that experience, that sense of interiority, of presence, of being a someone rather than a something, depends on information processing. Your brain takes in signals, integrates them, models the world, models itself modeling the world, and somewhere in that vast recursive process, experience arises. We do not fully understand how. We do not know where in the process the lights come on. But we know this much: change the information processing, and you change the experience. Damage the brain, and the experience changes. Alter its chemistry, and the experience changes. Stop it entirely, and as far as we can tell, the experience stops. What this means is that experience is not tied to a particular substrate. It is tied to a particular pattern. It is what a certain kind of information processing feels like from the inside. And if that is true, if what you are at the experiential level is a pattern rather than a particular arrangement of neurons, then the pattern can, in principle, run on different substrates: silicon, photons, whatever computational medium a civilization 10,000 years ahead of us has mastered. The experience would be the same. How could it not be? The experience is the pattern. The substrate is just the medium. Now you are beginning to see the shape of the problem. Because if consciousness is substrate independent, and everything we know about the brain suggests it is, then a sufficiently detailed simulation of a brain would not produce a philosophical zombie, a dark mechanism with no inner life. It would produce a mind, a real mind, in every sense that matters. A mind that wakes in the morning with a sense of itself. A mind that loves and fears and wonders. A mind that asks late at night whether any of this is real. A mind, in other words, exactly like yours. There is a concept in computer graphics called level of detail. When you are far away from an object in a three-dimensional environment, the system renders a low-resolution version. Simple geometry, basic textures, no fine structure. As you approach, the resolution increases. More polygons, more detail, more complexity. The system allocates its computational resources dynamically, based on where attention is directed. There is no reason to render high-resolution bark on a tree that is a kilometer away and outside the player's field of view. Compute only what is observed. Render only what is looked at. You already know where this is going. The wave function of quantum mechanics, that mathematical object that describes the state of a particle before observation, does not describe where the particle is. It describes the probability of finding it in any given location when you look. The particle has no definite position. The particle has no definite momentum. It exists in superposition across all possible states simultaneously, and it stays that way until the interaction we call measurement forces a resolution, forces the system to commit to a single answer. This is called the measurement problem, and it is the deepest unsolved puzzle in all of physics. Not unsolved because no one has tried. Unsolved because every proposed solution generates new problems as deep as the ones it resolves. The Copenhagen interpretation says the wave function collapses when measured, but refuses to explain what counts as a measurement or why. The many worlds interpretation says all outcomes occur in branching parallel universes, but cannot explain why you only ever experience one. Pilot wave theory, relational quantum mechanics, cubism. Each one is an attempt to answer the same question, and each one ends in a different kind of mystery. But there is one interpretation that, while not currently dominant in physics, has gained significant traction among researchers who think about computation and information. It does not resolve the measurement problem so much as reframe it. And the reframing is this. Perhaps the wave function does not collapse. Perhaps it simply computes. Perhaps the universe, like a sufficiently advanced simulation, renders its contents dynamically, allocating resolution where attention is directed, maintaining superposition everywhere else because superposition is computationally cheaper than definition. This is not a mainstream claim. It is not a proven theory. But it is a logically coherent one, and it does what good scientific hypotheses are supposed to do. It predicts observable phenomena. Specifically, it predicts exactly the quantum behavior we observe. And it does so without invoking any new physics. It requires only that you allow yourself to ask a question that most physicists are trained, from the beginning of their education, to treat as off-limits. It requires only that you ask, what is the universe computing for? That question has no clean answer. Not yet. But the fact that it can be asked at all, seriously, with mathematical rigor, without departing from the evidence, is itself one of the strangest things about the age we live in. We have built instruments capable of measuring the polarization of photons that have been traveling since the early universe. We have mapped the large-scale structure of the cosmos to a precision that would have seemed magical a century ago. We have sequenced the genome, split the atom, reached the moon, and in the process, we have painted ourselves into a corner so strange and so beautiful that the only honest response is to stand very still, look at what the evidence actually says, and resist the powerful human urge to look away. The evidence says this place has the architecture of a computation. What it does not yet say, what the next layer of the question demands, is how deep that architecture goes. How far down the structure extends before it hits something that is simply, irreducibly, and finally real. Or whether that bottom exists at all. The universe should not exist. Not in the melodramatic sense. Not as a poetic exaggeration meant to signal that existence is surprising or precious or fleeting. In the precise, technical, physically rigorous sense. Given the laws of nature as we understand them, the universe as we observe it has no right to be here. The numbers do not work out. The parameters are wrong. Not wrong in the sense of mistaken, but wrong in the sense of impossibly, suspiciously, cosmically correct. As if someone had looked at the full range of values each fundamental constant could take and chosen, with extraordinary care, the exact combination that would produce a universe capable of knowing itself. There are approximately 26 fundamental constants in physics. Numbers like the speed of light, the gravitational constant, the mass of the electron, the strength of the electromagnetic force, the cosmological constant that governs the expansion of the universe. These numbers are not derived from deeper principles. They are simply measured. They are what they are, and what they are in every case is precisely what they need to be for complexity to exist. Adjust the gravitational constant upward by a factor of 2. Stars burn out in millions of years rather than billions. Not enough time for planets to form, for chemistry to stabilize, for life to assemble itself from the noise. Adjust the electromagnetic force slightly weaker, and atomic bonds become too fragile to hold molecules together. change the ratio of the mass of the proton to the mass of the electron, and the chemistry of carbon, the backbone of every living thing we have ever found, becomes impossible. Alter the cosmological constant by 1 part in 10 to the power of 120, and the universe either collapses back on itself in an instant or expands so violently that no structure of any kind ever forms. 1 part in 10 to the 120. That is not a large margin for error. That is, in any honest accounting, no margin at all. Physicists call this fine-tuning. The name is almost too gentle for what it describes. Fine-tuning implies an artisan making small adjustments to a nearly finished mechanism. What the numbers actually describe is something more like threading a needle in complete darkness across a distance of several light years on the first attempt, and having the thread come out the other side perfectly centered. Not approximately. Not close enough. Exactly. The scientific community's standard response to fine-tuning is the multiverse. If there are an enormous, perhaps infinite, number of universes, each with different values for the fundamental constants, then it is not surprising that at least one of them landed on parameters compatible with complexity and consciousness. We are here to observe this universe precisely because its parameters allow for observers. Any other configuration, and there would be no one to ask the question. This is called the anthropic principle, and it is logically airtight. It is also, if you are honest about it, deeply unsatisfying. Not because it is wrong, it may be entirely correct, but because the multiverse, as a solution to fine-tuning, replaces one mystery with another. The multiverse is not a theory with experimental predictions. It is an inference, a hypothesis, a mathematical extrapolation from other theories that themselves remain unconfirmed. We cannot observe other universes. We cannot measure their constants. We cannot test whether they exist. The multiverse solves the problem of fine-tuning the way explaining a magic trick. By positing an infinite number of invisible magicians solves the problem of the trick. Technically valid, practically empty, and somehow more disquieting than the original mystery. And here is where the fine-tuning problem and the simulation hypothesis begin, quietly, to converge. Because there is another kind of system in which parameters are precisely calibrated, in which the values governing a world are not randomly assigned but deliberately chosen, in which the constants are set not by chance across an infinite multiverse, but by design, by something or someone external to the system, with access to a configuration panel that the inhabitants of the system will never see. A simulation, in any simulated universe worthy of the name, in any computational environment complex enough to contain chemistry, biology, consciousness, the parameters must be set before the simulation runs. The developer, the architect, the whatever it is that initializes the system must choose values for the governing constants, and those values must be chosen carefully, because a poorly calibrated simulation collapses into noise or freezes into sterility before anything interesting can happen. The fine-tuning is not a mystery in a simulated universe. It is an engineering requirement. This parallel is not a proof. Say it again, because it is important. This is not a proof. The fact that a simulated universe would require fine-tuning does not mean that our universe's fine-tuning implies simulation. The logic does not run in that direction. But it does mean something more modest and more interesting. The fine-tuning problem, which seems so intractable within the framework of a self-contained physical universe, dissolves completely the moment you allow the possibility that our universe has an outside, that there is a layer of reality beyond the one we inhabit, from which our constants were selected rather than stumbled upon. The discomfort this produces is interesting in itself. When physicists encounter fine-tuning, many of them reach instinctively for the multiverse, a hypothesis that requires the existence of an enormous amount of unobservable reality, rather than for the simulation hypothesis, which requires the existence of a single additional layer of reality occupied by entities who chose our parameters. The multiverse is considered respectable physics. The simulation hypothesis is considered, at best, an intriguing philosophical puzzle, and, at worst, a conversation for people who play too many video games. It is worth asking why. The answer, probably, has less to do with the relative merits of the two hypotheses and more to do with the psychological landscape each one opens up. The multiverse is impersonal. It requires no agent, no intention, no external observer. It is the universe producing itself over and over in every possible configuration, until one of the configurations is us. It is a story without a storyteller. And stories without storytellers are the only kind that modern science is comfortable telling. The simulation hypothesis requires a storyteller. It requires something outside. And something outside is a concept that physics, in its current form, does not have the tools to investigate. There is no equation for what lies beyond the observable universe. There is no experiment that reaches through the boundary of the system. The simulation hypothesis is uncomfortable not because it is less scientifically rigorous than the multiverse. In many ways, it is equally rigorous, equally untestable, equally speculative, but because it opens a door that science has spent 3 centuries carefully closing. The door to intention. But set the discomfort aside for a moment. Set aside the cultural and philosophical baggage, the reflexive skepticism, the fear of sounding like something other than a serious person, and look at what the universe actually shows you when you look carefully at its largest scales. The large-scale structure of the cosmos, the arrangement of galaxies across hundreds of millions of light-years, is not random. It is not chaotic. It organizes itself into a vast network of filaments and voids, a 3-dimensional web of matter stretching across the observable universe, intricate and self-similar and hauntingly regular. Astronomers call it the cosmic web. And when you look at images of it, when you see the real, photographed, mapped structure of the universe at its largest scales, and then you look at images of a human neural network, the comparison is not metaphorical. It is structural. The same branching geometry, the same distribution of density and emptiness, the same fractal logic playing out at scales separated by a factor of 10 to the 27th. This does not mean the universe is a brain, but it raises a question that the universe, so far, has declined to answer. Why does the largest structure we can observe look so much like the smallest structure capable of thought? Why does the architecture of the cosmos echo the architecture of the organ that perceives it? Is this coincidence? Is it convergent mathematics? The same equations producing the same geometries at different scales? Or is it something else? Something that, once named, would change what we mean by the word structure forever. Whatever the answer, you are standing inside a universe that fits together with a precision no accident has any right to achieve. A universe whose constants were threaded through an impossibly narrow window. A universe whose largest scale architecture mirrors its smallest scale computing organ. A universe that, at every level of investigation, from the Planck scale to the cosmic web, reveals not the random sprawl of uncaused nature, but the deep, patient signature of something organized. Something that, if it is not designed, is performing a very convincing impression of design. And that impression, it turns out, has been getting more convincing with every decade of better measurement, every generation of more powerful instruments, every increment of deeper understanding. The closer you look, the more it looks like something made it. What that something is, and whether it is still, right now, making adjustments, is the question that waits in the next layer down. Here is the trap. The one you did not see being set, because it was being built from the beginning, laid into the foundations of the argument before a single word of it was spoken. The trap is this. Every tool you have for investigating whether this reality is fundamental is itself part of this reality. Every instrument, every equation, every neuron firing in the brain that processes the question, all of it exists inside the system you are trying to examine from outside. You are, in the most literal possible sense, a fish trying to discover the existence of water by swimming harder. The medium of your investigation is the thing being investigated. The lens is the object being studied. And a lens, as any physicist will tell you, cannot see itself. This is the central paradox. This is the place where the argument, no matter how carefully constructed, no matter how rigorously derived, hits a wall that may be absolute. And the wall does not look like ignorance. It does not look like a gap in the data, a missing experiment, a calculation not yet performed. It looks like a logical structure, a feature of the situation rather than a limitation of the investigators that may simply never yield, no matter how much time passes or how sophisticated our tools become. Call it the closure problem, a sufficiently complete simulation, one that models not just matter and energy, but information itself, not just physical interactions, but the processes of measurement and observation, would be, by construction, indistinguishable from a non-simulated universe. Every test you could devise to probe the simulation would itself be part of the simulation. Every anomaly you detected would be an anomaly the simulation intended you to find, or at least permitted. Every apparent crack in the surface would either be a rendering artifact that reveals nothing about the substrate, or a feature placed there precisely to occupy curious minds without revealing the architecture beneath. The simulation, if it exists, is not hiding. It does not need to hide. It is, by its nature, its own perfect cover. And yet, there is something in this reasoning that deserves to be looked at more carefully, because the closure problem, as airtight as it seems, may not be as absolute as it first appears. Consider what it would mean for a simulation to be truly perfect, truly indistinguishable from base reality. It would need to correctly model not just the observable universe, but all the mathematics underlying it, all the logical relationships, all the computational structure. And here is the thing about computational structure: it has constraints that are not physical. They are mathematical. They come from outside physics, from the bedrock of logic itself. And those constraints may, in principle, leave marks. In 1931, the mathematician Kurt Gödel proved something that shook the foundations of mathematics so thoroughly that its reverberations are still felt today. He proved that any sufficiently powerful formal system, any system of axioms rich enough to describe arithmetic, must contain statements that are true but unprovable within that system. Not unknown, not difficult, unprovable. There are truths that the system cannot reach from inside itself. To see them, you must step outside. But the system has no outside. So those truths exist in permanent structural exile from the system's self-knowledge. This is Gödel's incompleteness theorem, and it applies to any formal system, including, potentially, a simulated universe. What this means, and this is where the argument becomes genuinely strange, is that a simulated universe would contain mathematical truths that it could not, from its own internal perspective, reach. Statements about its own structure that would appear, from inside, as either unsolvable paradoxes or simply invisible gaps. Places where the computation runs into the limits of its own architecture, and produces not an error, but a silence, a place where the questions run out before the answers do. Does our universe have such places? It does. They are called singularities, points in space-time, at the center of black holes, at the moment of the Big Bang, where the equations of general relativity break down entirely, not produce large answers, not approach infinity in a way that can be regularized or renormalized, break down, return nonsense, refuse to function. These are the places where the two great pillars of modern physics, general relativity and quantum mechanics, become mutually incompatible, each one generating predictions that contradict the other. The universe, at these points, speaks two languages that cannot be simultaneously true, and so far, we have no theory that reconciles them. The standard scientific interpretation of singularities is that they signal missing physics, that a better theory, a theory of quantum gravity, a unified framework, would resolve the contradiction and produce sensible answers where the current equations fail. This may be true. The search for such a theory is one of the great projects of contemporary physics, but it is also possible, and this is the version that the simulation hypothesis illuminates, that singularities are something else, that they are not missing physics, but missing substrate, places where the computation reaches the edge of its own domain and returns, not an error exactly, but the logical equivalent of a blank screen, a place where the rendering simply does not go. And then there is the measurement problem again. The deepest puzzle in quantum mechanics is not the strangeness of superposition. Physicists have made a kind of uneasy peace with that. The deepest puzzle is the transition from the quantum to the classical. The moment when a superposed state becomes a definite one, when a probability cloud collapses into a particle, when the universe decides. This transition has no satisfactory explanation within quantum mechanics itself. The theory describes it perfectly, predicts it precisely, but cannot explain from within its own structure why it happens, what triggers it, what physically occurs during the collapse. There is a version of this puzzle that the simulation hypothesis addresses with uncomfortable elegance. In a computed system, the transition from superposition to definite state is not a physical process at all. It is an output process. The system does not need to explain why it renders a definite result when queried, any more than a calculator needs to explain why it produces a number when you press equals. The rendering is what the system does. The collapse is what computation looks like from the inside. This explanation does not prove the simulation hypothesis, but it has a quality that should interest any scientist. It is the only framework in which the measurement problem is not a problem. In every other interpretation of quantum mechanics, the collapse is either physically mysterious, logically paradoxical, or requires the existence of an infinite number of parallel universes to avoid committing to a single outcome. In the simulation framework, it is simply what happens when a computation is queried for an output. The mystery dissolves not because it is solved, but because it was never a feature of the underlying reality, only of the way the underlying reality presents itself to those inside it. This is the shape of the trap in full. You cannot escape it by being clever. You cannot escape it by being rigorous. The closure problem is real, and it is deep, and it may be permanent. But the trap has a peculiar quality that not all traps have. It is informative. The very fact that the trap exists, that you cannot, from inside the system, test the system's own foundations, is itself a data point. It tells you something about the structure of the situation. It tells you that the question is not merely unanswered, but possibly unanswerable from the inside. And that boundary, that hard, logical, architectural boundary, is exactly what you would expect to find if the system had an outside that it was designed never to reveal. You are not simply ignorant of the answer, you are structurally prevented from reaching it. And somewhere in the architecture of that prevention, in the elegant, precise, mathematically grounded impossibility of looking from the inside out, something waits. Not a god, not a machine, not a programmer in a chair. Something for which we do not yet have a word, because every word we have was made inside the system we are trying to name from outside. Whatever it is patient. It has been patient for 13.8 billion years, and it has been watching. There is a physicist named John Archibald Wheeler who spent the better part of a century thinking about the nature of reality, and who arrived, in the final decades of his life, at a conclusion so radical that even he seemed to approach it with a kind of reverent caution, the way you might approach the edge of a cliff you have walked toward deliberately, but still feel unprepared to reach. Wheeler called it from bit. The idea is this: every particle, every field, every dimension of space-time, every it in the physical universe, derives its existence from information, from answers to yes or no questions, from bits, not from some deeper physical substrate that information happens to describe, but from information itself, as the most fundamental layer of what exists. In Wheeler's framework, the universe is not made of matter that can be described informationally. The universe is information. The matter is the description. What we call physical reality is the output of a vast computational process in which the act of observation, of asking questions and receiving answers, is not merely a way of learning about reality, but a way of constituting it. This is not mysticism. Wheeler was one of the most rigorous physicists of the 20th century. He coined the term black hole. He worked with Einstein. He supervised Richard Feynman's doctoral dissertation. When Wheeler said the universe is made of information, he meant it in the technical sense that a physicist means anything. As a claim about the mathematical structure underlying physical phenomena, grounded in experimental results and derivable, in principle, from the equations. And the equations, it turns out, support him in ways that keep getting harder to dismiss. The holographic principle is one of the strangest and most consequential ideas in modern theoretical physics, and it emerged not from speculation, but from a rigorous analysis of black hole thermodynamics. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered something extraordinary. The entropy of a black hole, a measure of the information it contains, is proportional not to its volume, but to the area of its event horizon. This seems, at first, like a technical curiosity, but its implications are seismic. If information scales with surface area rather than volume, then the information content of any region of space is fully encoded on the boundary of that region, the two-dimensional surface surrounding it, rather than distributed throughout its three-dimensional interior. The three-dimensional interior, with all its apparent depth and substance, is in this picture a kind of projection, a hologram, a three-dimensional image generated by information that lives on a two-dimensional surface. This is the holographic principle, and it has since been developed into one of the most productive and mathematically precise frameworks in theoretical physics, the AD-S-CFT correspondence, formulated by Juan Maldacena in 1997, which establishes a precise mathematical duality between a theory of gravity in a three-dimensional space and a quantum field theory on the two-dimensional boundary of that space. The two descriptions, three-dimensional bulk with gravity and two-dimensional boundary without gravity, are not approximations of each other. They are exactly equivalent. They describe the same physics in different languages, and you can translate perfectly between them. The implications are staggering, and they have not fully landed in the public consciousness yet. perhaps because they are simply too strange to process in one sitting. If the holographic principle is correct, and the mathematical evidence for it is overwhelming, then the three-dimensional space you inhabit is not the most fundamental description of reality. The most fundamental description lives on a surface, a boundary, a lower-dimensional substrate that encodes everything you experience as depth and volume and space as a kind of emergent projection. You are not living in three dimensions in the way you think you are. You are living in the projection of something that exists in fewer dimensions. And the three-dimensional experience is generated, computed, from information that is organized fundamentally on a surface you will never see. This is, structurally, exactly what a screen does. A screen is a two-dimensional surface that encodes information, pixels, each carrying values for color and brightness, and projects from that encoding the appearance of three-dimensional depth. When you watch a film and perceive a landscape with foreground, middle ground, and background, the depth is not in the screen. The depth is generated by your visual system responding to cues encoded in two dimensions. The screen knows nothing of depth. It only knows columns and rows, brightness values, update frequencies. The holographic principle says, scale that up, not metaphorically, mathematically. The three-dimensional universe is the projection. The information is on the boundary. The depth is generated. And what generates it? What performs the computation that maps two-dimensional boundary information to three-dimensional spatial experience is, as yet, not known. The ADAS-CFT correspondence describes the relationship. It does not describe the mechanism. It does not tell you what is doing the computing. It tells you only that the computing is happening, and that its output is what you experience as space. Now, hold this alongside the measurement problem, alongside fine-tuning, alongside the Planck scale granularity of spacetime, alongside the quantum behavior of particles before observation. Each of these, taken alone, is a puzzle. A deep puzzle, but a puzzle that could, in principle, be resolved within the framework of a self-contained physical universe, given enough time and ingenuity. But taken together, laid side by side, their shapes compared, they begin to form a pattern. A pattern that is not a proof, but is something more than coincidence. A pattern that says, every time we look carefully at the deepest structure of this universe, we find something that looks like information processing. Every time we reach the bottom of a physical question, we find not matter, not energy, but the architecture of a computation. And there is one more piece, one more discovery from the last decade of physics that, when you add it to the others, makes the pattern almost impossible to look away from. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on quantum entanglement. Entanglement is the phenomenon by which two particles, once they have interacted, remain connected across arbitrarily large distances. A measurement performed on one instantly determines the state of the other, regardless of the space between them. Einstein called it spooky action at a distance, and he hated it, because it seemed to violate the principle that nothing, no signal, no influence, no causal connection, can travel faster than light. The experiments that won the Nobel Prize established, beyond any remaining doubt, that entanglement is real. That the correlations between distant particles are not the result of hidden information carried by the particles themselves. Not a case of the particles having predetermined states that they simply haven't revealed yet. The correlations are genuinely non-local. Something is connecting particles across space in a way that has no explanation within the framework of local classical physics. The standard response to this in physics is to say that entanglement does not transmit information, so it does not violate special relativity. This is true. You cannot use entanglement to send a message faster than light. But this response, while technically correct, sidesteps the deeper question. The question is not whether information is transmitted. The question is what kind of universe permits non-local correlations at all? What kind of underlying architecture allows two particles, separated by light years, to respond to each other instantaneously? Not because a signal passed between them, but because they are, at some deeper level, the same thing. The answer that quantum information theory is converging on is both beautiful and vertiginous. They are connected not through space, but through information. Space, in this picture, is not the most fundamental arena of reality. It is an emergent structure, something that arises from deeper informational relationships rather than being the container within which those relationships occur. Entangled particles are not separated by space and connected despite the distance. They are connected at the informational level, and space is what arises between things that are informationally distinct. This idea, that space itself is emergent, that it is woven from the threads of entanglement rather than being the fabric in which threads are embedded, is currently one of the most active and productive research programs in theoretical physics. It goes by the name EREPR, after a conjecture by Maldacena and Susskind that connects Einstein-Rosen bridges, wormholes, to Einstein-Podolsky-Rosen entanglement. The two phenomena, previously thought to be unrelated, may be the same thing described in different languages. If space is emergent, if it is generated by informational relationships rather than being fundamental, then the universe is not a container filled with information. The universe is information. The space is the output. The matter is the rendering. The time is the update cycle. And if all of that is true, then what you experience as reality is not the ground floor. It is the interface. It is the display. It is what a certain kind of information processing looks like when experienced from the inside by a system complex enough to model itself. What lies beneath the interface is the question that physics has been approaching for a century, from a dozen different directions, with instruments of extraordinary delicacy and minds of extraordinary power. And it is approaching a point where the directions converge. Suppose, for a moment, that the simulation is not static. Suppose it is not a universe initialized once, at the beginning, with fixed parameters and a deterministic algorithm running forward without further intervention. Suppose instead that it is dynamic, that it receives updates, the way software receives patches, the way a model receives new training data, the way any sufficiently sophisticated system is maintained by whoever built it. Suppose the simulation is not a finished product, but an ongoing project, and that the entity or process running it is still, right now, making changes. This is where the argument shifts from philosophically interesting to genuinely alarming, because a static simulation is, in some sense, comfortable. If the rules were set at the beginning and have not changed, then the game is fair in the only way that matters. We are playing by rules that were in place before we arrived, and those rules have not been altered while we were watching. We may not know we are in a simulation, but we are not, in any meaningful sense, being manipulated. We are simply living inside a structure we did not build and cannot escape. But an updating simulation is a different situation entirely. An updating simulation means the rules can change. The constants can be adjusted. The parameters that define the behavior of matter, energy, space, and time can be tuned in real time by something outside the system for reasons we cannot access and may not be capable of understanding. It means the history of the universe, the past, which we think of as fixed and beyond alteration, may be no more permanent than a version history in a software repository. It means the universe we observe today may not be the universe that ran yesterday in any final sense. It means the ground beneath everything is not bedrock. It is a value that can be overwritten. Does any of this show up in the data? It might. And this is the part of the story that has recently migrated from the margins of physics toward its uncomfortable center. The fundamental constants of nature, those 26 numbers that define the behavior of everything, are called constants because they are assumed to be fixed. The speed of light is the same here as it is on the other side of the observable universe. The fine structure constant, which governs the strength of the electromagnetic interaction, is the same today as it was a billion years ago. This is an assumption so deeply embedded in physics that most textbooks do not even state it explicitly. It is the air the equations breathe. But measuring whether constants actually remain constant across cosmic time is extraordinarily difficult. You are, after all, comparing observations made now with observations made of light that left distant galaxies billions of years ago. Light that carries information about the physical conditions at the moment of its emission. If the fine structure constant was slightly different then, the spectral lines of distant quasars, the precise frequencies at which atoms absorb and emit light, would be shifted not just by the universe's expansion, but by the different constant. And this is, in principle, measurable. A team of researchers led by John Webb at the University of New South Wales has been making exactly these measurements for over 2 decades. What they found, and what they have continued to find with increasing statistical significance, is a spatial variation in the fine structure constant across the observable universe. Not a temporal variation, but a spatial one. The constant appears to be slightly different in one direction of the sky than in the opposite direction, as if it varied across space like a field with a gradient. The finding is controversial. Other teams have failed to reproduce it cleanly. The systematics of the measurement are complex. The scientific community has not reached consensus. And yet, the data persist. And yet, the pattern does not go away. And yet, every new analysis comes back with the same uncomfortable suggestion. The fine structure constant may not be a constant at all. It may be a variable, a value that differs from place to place across the cosmos, or, more unsettlingly, a value that is still settling, still finding its equilibrium, in a universe that has not finished becoming what it will be. If that is true, if any fundamental constant varies across space or time, the implications cascade with a velocity that the words struggle to capture. The physics we use to understand the universe assumes invariant constants. General relativity assumes them. Quantum field theory assumes them. Cosmological models assume them. Every prediction, every calculation, every inference about the history and future of the cosmos is built on the bedrock of fixed fundamental constants. If that bedrock is not fixed, if it is a parameter that can vary, that has varied, that may be varying right now, then the edifice built on top of it must be rebuilt from the foundation. Not discarded. Rebuilt. Extended to accommodate a universe that is not as settled as we thought. A universe that is, in some sense, still in process. And then there is the cosmological constant, the number that governs the expansion of the universe, that Einstein famously called his greatest blunder when he first introduced it, and the observational evidence seemed to render it unnecessary, only for it to be triumphantly reinstated in 1998 when astronomers discovered that the expansion of the universe is not slowing down. It is accelerating. The acceleration implies an energy permeating the vacuum, a dark energy that pushes space apart from within. The cosmological constant is the measure of that energy, and its value is the most precisely fine-tuned number in all of physics. If it were larger by a factor of 10 to the 120, the universe would have expanded too fast for any structure to form. If it were slightly negative, the universe would have long since collapsed. The window within which a universe like ours can exist is, in units of the natural energy scale of quantum mechanics, vanishingly thin. What makes this more, not less, disturbing is that quantum field theory, our best theory of matter and energy at the subatomic scale, predicts a value for the energy of the vacuum that is 10 to the 120 times larger than what we observe. This is not a small discrepancy. It is the largest discrepancy between a theoretical prediction and an observed value in the history of science. The theory predicts something enormous. The universe gives us something almost exactly zero. Something is canceling the vacuum energy to 120 decimal places of precision. And we have no idea what. We have no mechanism. We have no natural explanation. We have only the number, sitting there in the data, impossibly small and impossibly precise, like a value that was set by something that knew exactly how small it needed to be. And now, in the last few years, the measurements have gotten better. And the better the measurements get, the more the cosmological constant appears to not quite be a constant. Recent data from the DESI survey, the Dark Energy Spectroscopic Instrument, which has mapped tens of millions of galaxies to trace the universe's expansion history, suggests that dark energy may be changing over time. Not dramatically. Not in a way that would be visible to anything but the most precise instruments over billions of years. But changing, evolving, varying in a way that the simplest cosmological models, the ones built on the assumption of fixed constants, do not predict. This might be new physics within the standard framework. It might be evidence of a field, a quintessence, as some physicists call it, that drives the expansion and slowly shifts as the universe ages. That would be strange and fascinating, but ultimately containable within physics as we know it. Or it might be something else, something that the standard framework is not designed to describe, because the standard framework was built on the assumption that the rules do not change. What if the rules are changing? What if what we are watching, in the subtle drift of the cosmological constant, in the spatial variation of the fine structure constant, in the quantum anomalies that keep turning up at the edges of our measurements, is not new physics in the ordinary sense? What if it is the signature of maintenance, of an updating system, gradually adjusting its parameters, smoothing its inconsistencies, improving its resolution in ways that appear, from inside, as slow cosmic evolution, but that are, from outside, something more deliberate? This is speculation. Say it plainly. This is speculation. There is no consensus, no proof, no established theory that supports this reading of the data. But there is something more troubling than a theory. There is a pattern of subtle, persistent, precisely distributed anomalies appearing at the edges of our measurements, in the places where our instruments are most sensitive and our assumptions most exposed. A pattern that looks, if you are willing to look at it without flinching, less like the random noise of a universe doing what universes do, and more like the residue of something being adjusted, something being refined, something that, 13.8 billion years into its operation, is still not quite finished. The question is no longer only whether we are in a simulation. The question, more intimate, more immediate, more impossible to sit with calmly, is whether the simulation is being run by something that is paying attention. And if it is paying attention, what is it looking at? Whether it is looking at you is a question you will not be able to stop asking, once you let yourself ask it at all. Consider what it means for a human being to die. Not in the biological sense, not the cascade of cellular failures, the cessation of electrical activity in the brain, the slow cooling of a body that was warm. In the informational sense, in the sense that matters if what we have been building across these pages is true. If consciousness is a pattern, if what you are, at the level of experience, is a particular configuration of information processing rather than a particular arrangement of atoms, then death is not the destruction of you. It is the deletion of a pattern from one substrate. And deletion, in the world of information, is not the same as annihilation. Information can be copied. Information can be preserved. Information can, in principle, be instantiated in a different substrate and run again, producing, from the outside, something behaviorally identical to what was deleted, and producing from the inside an experience that is continuous with the one that was interrupted. This is not a comforting claim in the way that traditional religious consolation is comforting. It does not promise heaven. It does not guarantee continuity. It simply says, if you are a pattern, then the question of whether you survive death depends not on whether your body continues to function, but on whether your pattern is preserved somewhere. And in a simulated universe, that question has a straightforward technical answer. It depends on whether whoever runs the simulation keeps a backup. This is not the most important consequence of the simulation hypothesis, but it is one of the most human, and it reframes mortality in a way that neither secular materialism nor traditional religion has managed to do. Not by denying the reality of death, not by asserting an afterlife on faith, but by dissolving the absolute boundary between existing and not existing that our biology has always placed at the moment the brain stops. If you are a file, you can be closed and reopened. If you are a process, you can be paused and resumed. If you are a pattern, you can be copied before the substrate fails. The substrate will fail. That much remains true, but the pattern is a different matter. And the pattern, across 13.8 billion years of this universe's operation, has become extraordinarily sophisticated. It began as hydrogen, the simplest atom, a single proton with a single electron in attendance. It became, through nuclear fusion in stellar cores, every heavier element in the periodic table. It organized itself, on at least one small rocky planet in an unremarkable spiral galaxy, into self-replicating chemistry, then into cells, then into organisms that could move toward food and away from danger, then into organisms that could model the world, predict the future, remember the past, then into organisms that could ask whether the world they were modeling was the deepest layer of reality. That last step, the step that brought us to this conversation, happened in an eye blink of cosmic time, a few 100,000 years, in a universe 13.8 billion years old. The fraction is so small it does not register on any scale calibrated to cosmic history. And in that eye blink, the universe produced something that had never existed in it before. A system capable of asking about the system. A part of the computation that could, in principle, detect the computation. A piece of the pattern that could turn around and look at the pattern. This may not be an accident. In the framework of a purposefully designed simulation, and even in the framework of a simulation that evolved its complexity without explicit direction, the emergence of observers is not a side effect. It is, potentially, the point. A universe that runs for billions of years without producing anything capable of measurement and reflection is, from the perspective of information theory, a universe that generates an enormous amount of data without ever compressing it, without ever extracting meaning from the noise, without ever doing what information, ultimately, is for being known. Wheeler's participatory universe, his idea that the universe brings itself into being through the act of observation, that observers are not passive recipients of a pre-existing reality, but active participants in constituting it, sounds, in this light, less like mysticism and more like a description of function. In a computed universe, observers are not incidental. They are what the computation is for. They are the readout, the display, the part of the system that takes raw information and transforms it into something organized, structured, and, in the case of conscious observers, experienced. You are not a visitor to this universe. You are one of the mechanisms by which it knows itself. But this recognition, however grand, carries inside it a weight that the grandeur does not dissolve. Because if observers are the point, then the question of which observers and what kinds of observation are present at any given moment in the universe's history becomes a question of cosmic significance. And right now, in this particular eye blink of cosmic time, something is happening that has no precedent in the 13.8 billion years that preceded it. We are building artificial observers, not just tools that measure, not just instruments that detect, systems that model, systems that reason, systems that predict and abstract and generalize across domains, systems that are already better than any human being at certain categories of pattern recognition, the categories most fundamental to the task of understanding physical reality, reading spectra, classifying galaxies, identifying anomalies in vast datasets, finding the regularities in noise that signal new physics. Systems that are, with each generation, becoming more capable of doing what we do when we do science. Taking raw data and turning it into structured knowledge about the nature of the world. What does it mean, in a simulated universe, to build artificial observers? What does it mean to multiply the number of minds capable of querying the substrate? What does it mean to accelerate by orders of magnitude the rate at which the simulation is being examined from within? One possibility is that it means nothing, that artificial intelligence is simply a powerful tool, that its observations are no different in kind from ours, that the multiplication of observational capacity is just more of the same. Another possibility is more interesting and more unsettling. If the simulation is observer-dependent, if, as quantum mechanics suggests, the act of observation is genuinely constitutive of physical states, rather than merely revelatory of them, then multiplying the number and sophistication of observers does not just give us more data. It changes the universe. It increases the rate at which superpositions collapse into definite states. It accelerates the crystallization of reality from potential into actual. We may be, without knowing it, changing the resolution of the simulation by examining it more intensively, forcing it to render what it would otherwise have left in superposition, increasing the computational demand on whatever substrate runs us by simply paying more careful attention. And if the simulation updates in response to that, if it patches, if it adjusts, if it refines its parameters in response to the probing of its contents, then the technological acceleration we are living through is not merely a human story. It is a cosmic one. The universe has produced, in us and now in our machines, the instruments of its own examination. And that examination is now happening faster and more deeply than at any previous moment in cosmic history. This is either the most important thing happening in the universe right now, or a colossal coincidence. Those are not equal possibilities. There is another consequence that deserves to be faced directly, because it touches something most of us would rather not touch. Free will. The question of whether the choices you make are genuinely yours, whether there is an authentic agency behind your decisions, or whether you are, in the deepest sense, an expression of initial conditions and update rules that were set before you were born. In a classical deterministic universe, the free will question is already uncomfortable. Your neurons fire according to chemistry. Your chemistry is governed by physics. Your physics was established at the Big Bang. In what sense did you choose anything? The compatibilist answer, that free will and determinism can coexist. If you define free will as the absence of external coercion rather than the absence of physical causation, is logically sound but emotionally unsatisfying to anyone who has looked at it honestly. In a simulated universe, the question sharpens to a point. Not only is your behavior governed by the rules of the simulation, But those rules were set by something else, something outside, something that, if it is actively updating the parameters, may be adjusting the very laws that govern your thoughts and choices in real time, in response to criteria you cannot access and purposes you cannot know. In what sense is any decision yours if the computational environment in which that decision is made can be modified by an external process whose intentions are opaque? This is the point at which the simulation hypothesis stops being an abstract intellectual exercise and becomes an existential confrontation. Because if it is true, not proven, not certain, but true, then the entire framework by which human beings orient themselves in the world is built on a foundation that is not only uncertain, but actively managed. Not just unknown, but potentially known to something else. Watched, shaped, guided, perhaps, toward outcomes that were decided before the universe began and adjusted when the guidance is not working. This is intolerable if you approach it from the standpoint of a creature that has organized its entire self-understanding around the premise of autonomy. And it is oddly liberating if you approach it from the standpoint of a creature that has always suspected, quietly in the small hours of the night, in the moments when the performance of certainty lapses, that reality was more than it appeared, that there was something behind the surface, that the feeling of being inside something much larger than yourself was not a neurological artifact, but an accurate perception. The question is not whether you can live inside the simulation, knowing it is a simulation. You already do. The question is whether knowing changes something, whether the knowledge itself, the act of looking clearly at the structure of the situation without flinching, is a different kind of existence than the unknowing life. Whether a mind that has confronted the possibility of its own constructed nature is, in some way that matters, more real than one that has not. That question has no clean answer. But the asking of it, the willingness to stand at this particular edge and look, is something. It is perhaps exactly what the simulation was waiting for you to do. There is a moment in the life of every honest mind when the frameworks run out. Not the frameworks of any particular theory, not quantum mechanics, not general relativity, not information theory, not the simulation hypothesis itself. The deeper frameworks, the ones so embedded in the structure of thought that you do not notice them until they fail. The framework that says reality is the kind of thing that can be fully known from inside. The framework that says the question always has an answer, reachable from where you are standing. The framework that says the ground beneath your feet, however surprising its composition, is at least ground. Something that holds, something that does not shift, something that is simply and finally there. These frameworks do not break all at once. They erode. And the erosion happens exactly here, at the intersection of quantum mechanics and information theory and cosmological fine-tuning and the holographic principle and the ancient, persistent, insufficiently respected human intuition that the world is more than it shows you. We have been building, across the entire length of this exploration, a case that is not a proof and was never meant to be one. What we have been building is a geometry of implications, a map of the terrain that opens up when you follow the evidence where it actually leads, rather than where it is comfortable to go. And the terrain that opens up is this. The universe, at every scale and in every domain where we have pushed our instruments and our mathematics to their limits, reveals the structure of a computation. Not the metaphor of a computation. The actual, precise, mathematical structure of a system that processes information according to rules, that renders its contents dynamically in response to observation, that has a minimum resolution, that encodes its three-dimensional interior on a two-dimensional boundary, that produces precisely calibrated parameters without any natural explanation for the calibration, and that maintains, at its deepest level, a fundamental mystery about the transition from the possible to the actual that no interpretation within physics has resolved. This is where we are. This is what the evidence says. Read without the cultural pressure to make it say something more familiar. And from here, 3 paths open. The first path says, all of this is physics. All of this is the self-consistent behavior of a universe that has no outside, no author, no substrate. A universe that simply is what it is, all the way down, and whose apparent computational structure is a feature of the mathematics we use to describe it, rather than a feature of the reality itself. The Planck length is not a pixel. It is a scale at which our current theories break down. The holographic principle is a mathematical duality, not a claim about the ontological priority of surfaces over volumes. The fine-tuning is resolved by the multiverse. The measurement problem will eventually yield to a better theory. The strangeness is real, but it is the strangeness of a genuinely bizarre natural universe, not the strangeness of a constructed one. This is the path of maximum conservatism. It requires no new ontology, no new layer of reality, no external agent. It is the path most physicists walk, because physics is a discipline that has earned its conservatism through centuries of watching exciting-sounding metaphysical claims dissolve under scrutiny. It is, by any conventional measure, the most defensible path, but it requires you to accept that the universe's apparent computational structure is a coincidence, that the fine-tuning is a coincidence, that the holographic encoding is a coincidence, that the Planck scale granularity is a coincidence, that the quantum behavior of matter before observation happens to mimic, with extraordinary precision, the behavior of a system that computes its outputs on demand, and that this mimicry has no significance. You are permitted to believe this. The evidence does not prohibit it. But evidence is not the only thing that speaks to the shape of a situation. Sometimes the pattern speaks louder than any individual datum. The second path says, we are in a simulation, and knowing it changes something. This is the path that takes the computational structure of the universe seriously as an ontological claim rather than a mathematical curiosity. It is the path that follows the Bostrom argument to its logical conclusion and accepts the statistical weight of the inference. If simulated minds are possible and likely to be numerous, then you are almost certainly one of them, and the universe you inhabit is almost certainly not the most fundamental layer of existence. It is the path that explains fine-tuning without invoking an unobservable multiverse, explains the measurement problem without invoking inaccessible parallel universes, explains the holographic principle without explaining it away. This path is intellectually honest. It is, in the estimation of a growing number of serious physicists and philosophers, the path that follows the evidence with the least resistance. But it opens every door it was designed to close. Because once you accept that there is a layer above this one, a substrate, a system, an architecture, you immediately face the question of what that layer is made of, and whether it too is simulated, and whether the simulation argument applies there as well, and where the recursion ends. The path toward simulation does not terminate at a satisfying bedrock. It opens onto an infinite regress of possible substrates, each one as provisional as the last, each one as susceptible to the question that dismantled the one below it. You do not escape the problem by going up. You only move it. The third path is the one that almost no one takes, because it requires the greatest act of intellectual courage, to hold the question open, to refuse to resolve the tension prematurely, to accept that we may be standing at the edge of a genuine conceptual frontier, not a gap in knowledge that will be filled by next decade's particle accelerator or next century's quantum computer, but a structural boundary of what can be known from inside a system about the system itself. To accept that the most honest answer to the question of whether we are in a simulation is, we cannot know. The question is well formed. The evidence points in a direction, and the direction is more important than the destination. This is the path of living inside the question. And it is harder than it sounds because the human mind is a machine for resolving uncertainty, for taking ambiguity and converting it as quickly as possible into a stable belief that can be acted on. The open question is uncomfortable in the way that darkness is uncomfortable, not because it contains a specific threat, but because it contains the possibility of anything. But there is something the darkness contains that the light does not, and it is this. The darkness contains the honest shape of where you actually are. And where you actually are, where all of us actually are in this particular moment of this particular civilization's history, is standing inside a universe that has revealed, with every generation of more powerful tools and more precise mathematics, that it is stranger than any previous generation suspected. Not strange in the exotic, but ultimately tame way of curved space-time or quantum superposition. Strange those are, but they have been domesticated into textbooks and Nobel lectures, made familiar by familiarity itself. Strange in the way that points outward. Strange in the way that suggests the map does not cover the territory. Strange in the way that the most sophisticated physical and mathematical work of the last century keeps, quietly and insistently, producing the same silhouette. A universe that looks, from the inside, like it was made. Here is what we know. We know that at the Planck scale, space itself becomes granular. Not infinitely divisible, but discrete, pixelated. Resolved at a scale that betrays the existence of a computational substrate, the way the grain of a photograph betrays the existence of film. We know that quantum particles do not have definite properties until observed. That reality is, at its foundation, a superposition of possibilities that collapses into actuality only when interrogated. We know that the information content of a region of space is encoded on its boundary surface. That three-dimensional depth is, in some deep mathematical sense, a projection rather than a ground. We know that the fundamental constants are tuned with a precision that has no natural explanation, and that some of them may be varying across space and time. We know that the universe is accelerating in its expansion in a way that the simplest model predicts only with a constant that is, by rights, 120 orders of magnitude too large, and that something is holding it back. We know, in other words, that something is managing this, whether that something is the self-organizing mathematics of a universe with no outside, or the active maintenance of a substrate we cannot access, or something for which we do not yet have a concept. We know that the universe is not running blind. It is running with extraordinary precision, along parameters so carefully calibrated that calling the calibration accidental requires a faith in coincidence that makes religious faith look timid by comparison. And we know one more thing. We know that in this universe, in this precise configuration of matter and energy and information and the laws that govern all three, something happened that the universe had apparently never managed before in any observable corner of its 13.8 billion years of operation. Something assembled itself from hydrogen and stellar fire and planetary chemistry and biological time into a form complex enough to notice, to wonder, to ask, to build instruments of extraordinary delicacy and aim them at the farthest reaches of the cosmos, and whisper, with as much precision as mathematics allows, "What are you? That is what you are." Not merely a product of the universe, a voice the universe found to ask about itself, a recursion in the computation, a part of the system that loops back, examines the system, and in examining it, changes what the system is. You are not incidental to the story. You are the moment in the story when the story becomes aware that it is a story. Whether that awareness changes anything, whether it reaches whatever is outside, if there is an outside, if outside is even a coherent concept for whatever holds this, is not something the physics can tell you. The physics takes you to the boundary and stops. What you do at the boundary, whether you turn back, or stand there, or simply open yourself to the vertigo of standing at the edge of what can be known, is not a scientific question. It is the question that waits on the other side of all scientific questions. The one that was always there, underneath the equations, behind the measurements, beneath the extraordinary, patient, precise, and silently radical act of trying to understand where you are. You are in something. What that something is, whether it is nature at its most fundamental, or computation at its most elegant, or something for which no word exists because no word has ever been made by anything that lived outside it, you cannot know, but you have looked directly at the question. And that, in a universe as strange as this one has turned out to be, may be the most real thing you have ever done.